Imagine sending a robotic probe deep into an uncharted galaxy. It's light years away, making remote control from Earth physically impossible. Out there, the environment is entirely unpredictable. Human engineers can't write a traditional instruction manual for every rogue asteroid, cosmic dust cloud, or alien gravity well the probe might encounter. To survive, the probe needs something more flexible than a rigid script. It needs the ability to take in new information, recognize patterns, and make its own decisions. When you can't predict what's coming in the deep void, autonomous decision-making becomes the only viable way to safely navigate the unknown. Traditional programming relies on an explicit list of rules, but when it encounters unexpected input, the logic breaks. Machine learning takes a different approach. We feed it examples, letting the algorithm figure out the underlying patterns on its own. To build a capable explorer, we equip our probe with 3 distinct learning modules: supervised learning, unsupervised learning, and reinforcement learning. Shifting our focus from dictating strict rules to providing rich experiences is the core building block of modern artificial intelligence. The first phase of training happens before the probe ever leaves the launch pad. This is supervised learning, and you can think of it like studying from a massive deck of carefully labeled flashcards. Engineers feed the system millions of images of known celestial bodies. Every single image has a specific tag attached, like star, planet, or asteroid. You point to a photo, say cat, and repeat until the child identifies the animal without help. To establish those initial patterns, the algorithm absolutely requires both halves of the equation, the raw input data and the correct output labels. This table of data shows the relationship between multiple descriptive attributes on the left, like sky conditions or temperature, and a final target concept on the right. By looking at these patterns, the model learns to map specific observations to a definitive outcome. Because it relies on human-provided historical truth, supervised learning is highly effective at making accurate predictions about things we already understand. But eventually, our probe travels beyond mapped space and glides into a bizarre nebula filled with alien matter. There are no historical records here. The database has no labels for what it's seeing. This is where unsupervised learning takes over. Instead of checking its work against a list of correct answers, the machine is forced to look at the raw data and find hidden structures on its own. If you've ever tried sorting a massive pile of puzzle pieces without looking at the box cover, you've done this. You naturally start grouping pieces together by shared colors or similar shapes. The machine scans the chaotic environment, clustering objects, separating lightweight glowing blue rocks from dense ones. This is k-means clustering, a mathematical technique that finds natural groups by measuring distance between items and assigning them to the nearest central point. Unsupervised learning will never give the glowing blue rock a specific name. It simply reveals how that rock relates to everything else in the chaotic dataset. Finally, the probe drops a specialized rover onto the rocky surface of an unmapped exoplanet to navigate across a treacherous deep crater. To do this without a map, the rover uses reinforcement learning. Under this framework, the machine treats navigation like a game, driven entirely by trial and error. The environment is built around a digital scoring system. The rover receives a positive reward point for moving closer to its target destination, and a negative penalty point if it hits a wall or falls into a ditch. It operates on the same logic as training a dog. You give them a treat for performing the correct action, and you withhold the treat when they make a mistake. Because it's a computer, the rover can run millions of rapid, virtual simulations of the crater in a matter of seconds, trying out every possible route until it discovers the most efficient path to its destination. Through relentless experimentation, reinforcement learning excels at finding optimal strategies in environments that are constantly shifting. We don't need to travel to deep space to see these algorithms at work. They are already running on the devices in your pocket. That initial supervised learning approach we talked about, that's your email filter, carefully studying millions of labeled messages so it can identify and block incoming spam. Unsupervised learning powers your favorite streaming service. It looks at your viewing habits, clusters you together with similar users, and naturally recommends a movie you're likely to enjoy. And reinforcement learning is what allows the sensors on self-driving cars to process unpredictable city traffic and navigate safely to your driveway. These systems have mastered our most complex strategy games, but that skill is simply a byproduct of their ability to solve practical human problems. Machine learning is not magic. It is simply the rigorous process of transforming raw experience into actionable intelligence, making it our most powerful tool for exploring the unknown, whether that's out in the cosmos or right here at home.